Hello, this lesson is on psychrometrics. You can find relevant equations that we'll discuss and the psychrometric chart in your reference handbook section labeled Psychrometrics. Let's get started. Atmospheric air is a mixture of dry air and water vapor, and individually we can treat these as ideal gases. And the psychrometrics is the study of water vapor in air. Now, we know that we can always treat dry air as an ideal gas because we were taught that it's made of nitrogen and oxygen and argon. Those are all ideal gases. But you may remember from thermo class that steam, water vapor, really shouldn't be treated as an ideal gas. Well, we're going to make an exception in this time because the water vapor is at very, very low pressures, low partial pressures, and the temperatures are such that the ideal gas assumption is pretty close, and we can treat it as an ideal gas, which makes life a lot easier for us in the HVAC world. Part of that is that we can talk about the total pressure of the air. And the total pressure is the partial pressure of the dry air, all those components added together, plus the partial pressure of water vapor. And so we can add those together, and that will give us our total pressure. The study of psychrometrics involves three important temperatures that you're going to see on your test, and you'll see in HVAC in general. And they're denoted as follows: T, dry bulb temperature; T star, wet bulb temperature; and TD, dew point temperature. Now I prefer to use capital letters for temperatures, and I prefer to use WB and DP as my subscripts for wet bulbs and dew points. But this is what the reference handbook uses, and so we're going to stick with their terminology and their listing because it will just help reduce confusion. The dry bulb temperature is the temperature a regular thermometer measures. So if you look on the thermometer on the wall and you look at it and it says 75 degrees, that's what the dry bulb temperature is. The wet bulb temperature is obtained from what we call an adiabatic saturation process. Well, that's just a fancy way of saying we're going to add water vapor to air, and that air will cool because of evaporation. But we're not going to take any heat out of the box. We're not going to remove any heat from the system. We're going to let all the cooling happen because of evaporation and evaporation only. And so the air and the water cool as some of the water evaporates into the air. And then that process stops when the air is completely saturated. And the temperature at where it stops is known as the wet bulb temperature. We can get that from a device called a Sling Psychrometer. And there are electronic devices that can do it too. The dew point temperature is the temperature at which condensation would begin if the air is cooled at constant pressure. So TD is Tsat at the partial pressure of water vapor. So you could look that up on a steam table. Now the steam tables in your reference handbook are actually pretty good. They're not split out in 5 or 10 degree increments, but in smaller increments. And that'll help you when you're looking at that and thinking about interpolating. You won't have to do that as much. Looking at the TS diagram, we can see steam. We can see the steam dome. The green is the saturated liquid line. The red is the saturated vapor line. And then I can draw lines of constant vapor pressure, constant pressure of water vapor. I can plot a temperature, and I'll just put that on my constant pressure line, T. And it's not saturated. It's actually in the superheated region. So that means that we're not completely saturated. Then we can draw an adiabatic saturation process, and it will look something like that, the dashed line that just came up. And so when we finally saturate the air completely, we intersect with the red saturated vapor line, and that temperature is called the wet bulb temperature, or T star. I can also find the dew point temperature on this plot by following the constant pressure line down until it intersects the saturated vapor line. And that temperature, where that intersection occurs, is known as my dew point. Now that's the thermodynamic way to find dew point. We can also find the dew point and think about dew point slightly differently. If we have air outside that we're looking for the dew point, we can think about, well, how much do I need to cool that air outside, seeing that the pressure outside doesn't change a lot, until I get dew forming, until I have dew on the grass or dew on my car. That's the dew point temperature. We can also talk about absolute and relative humidity. And this is the amount of water vapor in atmospheric air. And so there are two ways that we can talk about this. So we have the absolute or specific humidity. It's also called the humidity ratio. A lot of names for that. And we can also talk about the relative humidity. The absolute or specific humidity is defined as the ratio of the mass of water vapor to the mass of dry air. So humidity ratio is W, and the reference handbook uses capital W instead of little w or the Greek omega. And it says MW over M dry air. So it's a ratio of masses. Now it's not quite the percent by mass. If it were percent by mass, the denominator would be total mass of dry air plus mass of water. In all of our air conditioning and psychrometric analysis, we're going to reference everything to the mass of dry air. And that's really important to remember. And there's a reason behind that, and I'll talk about that in just a few minutes. Since both the water vapor and air act as ideal gases, we can play some games with these masses, and we can convert these masses into pressures. So we know from the ideal gas law that M equals PV over RT. You might have seen this as PV equals nRT, with N being the number of moles. But I can manipulate moles and I can get mass with that, with the molar mass. It's just a matter of changing what that R is. So R in this relationship is the R for the particular gas, R universal divided by molar mass, if you're interested in the details. And I can plug that into my specific humidity relation, and I get a whole bunch of terms here, P's and V's and R's and T's, each depending on whether it's water or dry air. Now I recognize that the water vapor and the dry air exist in one volume, and they exist at one temperature. And so what I can do is I can actually cancel those out. The volumes and the temperatures cancel out since they're the same. And I'm left with nothing but ratios of R's and partial pressures. Now, knowing that the R is R universal over the molar mass, the R universals also cancel out. And then I'm left with ratios basically of molar masses and partial pressures. Now, the molar mass of dry air is about 29, and the molar mass of water is about 18. And so if I plug those numbers in and massage things up a little bit, I get W is 0.622 PW over P dry air. And knowing that the total pressure is P of the dry air plus P water vapor, I get my final relationship. W is 0.622 times the partial pressure of water vapor divided by total pressure, which is what we measure oftentimes, minus the partial pressure of water vapor. Now remember, the partial pressure of water vapor is going to be 0 if the air is completely dry, and it's going to be P sat at the temperature when it's saturated. So you can find the saturation of partial pressure of water vapor if you go into your steam tables and look at what P sat is at the temperature. And the partial pressure of water vapor is always going to be somewhere between those two. If the mass of water vapor in the air is divided by the maximum amount of water vapor the air can hold, then we can talk about relative humidity. It's relative to what's the maximum amount of water vapor the air can hold. How saturated is the air mass, in other words. And so phi is the ratio of the mass of the water vapor that we have divided by the mass of water vapor at saturation. And I can throw in my ideal gas law again and play some games, knowing that the molar mass of water and RW basically cancel out, as does V and T. And I can say that the mass ratio is equal to the pressure ratio, PW over what the vapor pressure would be at saturation. So we can calculate our relative humidity that way. And relative humidity is always between 0 and 1, between 0 and 100%. Can't really have a relative humidity over 100%. And it's not very stable if you ever find that. Combining these expressions, we come up with another relationship for W that's based on the relative humidity rather than in the saturation vapor pressure, rather than just the vapor pressure we actually have. And so we can write that. Sometimes that's a useful relationship to have. It may be useful for a problem. I prefer just to do the two steps, but sometimes some people like to have that relationship, and so there it is. The adiabatic saturation process we talked about a little bit before. It's a difficult thing to do, but we can use a Sling psychrometer. That's a really hard thing to say, you know. And that's what we've historically used in the past to measure these wet bulb temperatures. But electronic devices today provide more accuracy, and it's a lot easier to use. And so basically what a Sling psychrometer has, if you've ever seen one, is there's two thermometers on that. One of them is for the dry bulb temperature, and it's just a regular old thermometer like you'd see. And then the second one has a wick on it. And the idea is that you wet that wick, you get it saturated with water, and then you take these two thermometers and you wave them around in the air. A lot of them have a handle and a little pivot, and basically you just sling this thing around like a party favor. And when you sling it around, you're basically moving a lot of air over that wet thermometer wick, and you get an evaporation process occurring. And so at the end, after you've waved it around a minute or two, you read the two thermometers. The one that's dry is the dry bulb temperature. The one that is wet is, well, the wet bulb temperature. That's exactly where all this comes from. And so, yes, so we sling it around and we create an evaporation effect on the water. And that's how we used to measure it. Nowadays, what we do is we just use an electronic device, and it will do something with like capacitance of the air or something to figure out how much moisture is in the air. And then it'll use lookup tables and relationships that are built into the little chip in the device, and it'll tell us what the dew point is, tell us what the wet bulb temperature is, what the relative humidity is. It does the calculations for us. And the drier the air, the lower the wet bulb temperature is going to be. And so if you think about that for a second, that makes sense. If I start off with air that's at 75 degrees and pretty moist, I really can't add a lot of water to the air before I reach saturation, and so I can't cool it much. But if I start at 75 degrees in the desert where it's very, very dry, I can add a lot of water vapor to the air before I reach saturation. And that produces a tremendous amount of cooling. And so the wet bulb temperature in the desert would be lower than the wet bulb temperature in the east, say, where it's a lot more humid. Starting with the same dry bulb temperature. Okay, so now let's talk about enthalpy. And so we have the total enthalpy of the air-water mixture, capital H. And it's going to be the H of the dry air plus H of the water vapor added together. So we add the energies together, just like we add the masses together and add the partial pressures. I can write that as mass of the air times little h of the dry air, that's specific humidity, BTUs per pound, kilojoules per kilogram, whatever your favorite unit is, plus MW HW. And now we can play some algebra with this. We can divide through by the mass of dry air, MA, or MDA, and we can end up with the relationship that the enthalpy of the mixture, little h, is going to be little h of the dry air plus the specific humidity, the humidity ratio, times h of the vapor. And then we can find those two separately, those two enthalpies separately. Now, h of the air is going to be Cp times the temperature. And h of the water vapor is going to be either h of saturated vapor, if we're completely saturated, or HFG plus CP times the temperature. So if we have superheated vapor, if we are not saturated, the water vapor in the air exists in a superheated condition, above saturated conditions. And so we'll add Hg, and then we'll add Cp times T. We'll add the amount of superheat to that. Now you may notice that we have a temperature here, just a single temperature here, but we're not necessarily having to use absolute temperature. And that's because the thermodynamics people were really clever, and they said, you know, let's reference everything to 0 degrees Fahrenheit. And when you do that, the T reference is 0, and it basically goes away. And so completely dry air at 0 degrees Fahrenheit is defined to have an enthalpy of 0. Can you have negative enthalpies? Absolutely. Happens all the time in Alaska and in the Arctic. Temperatures are below freezing, you don't have a lot of water vapor in the air, enthalpy is negative. That's fine. It's just saying that the enthalpy is less than the reference value. So we don't have to convert temperatures. Now, a word of warning, if you read tables that are in SI units, they're going to be a bit different than tables that are written for American or imperial units, because they may use a different reference temperature. They may use 0 Celsius as their reference temperature. So be careful if you're switching between unit systems. So basically, all these relationships make it so that we can calculate things, but you know, engineers are lazy. And so what we've done is we've created a psychrometric chart, which allows us to do all these things without having to do a lot of calculations. And so the standard chart is for sea level and at normal temperature range, something you see in air conditioning world. And they have charts that are for low temperatures and high temperatures, as well as for elevations, 5,000 feet, 10,000 feet. So if you're in Denver, you might use the psychrometric chart for 5,000 feet, or Mexico City would be 10,000 feet, I believe. Most of the problems are going to be for sea level, and if you're somewhere near sea level, those will work just fine. Your reference handbook has charts for other temperature ranges, high and low, as well as for other elevations, and so you may find those useful. Be sure to read your problem to make sure that you're selecting the right chart. So the chart is basically an XY chart, and you'll see along the x-axis, along the bottom, we have dry bulb temperature. So anytime we change temperature, we're going to move left to right. And then on the y-axis, we have specific humidity. Think about that as just the amount of water vapor in the air, the number of molecules of water. And so to specify a point, we need 2 coordinates. We need an x and we need a y. And then once we have that, we have a point on that chart, and we can read everything else. And so the psychrometric chart is going to have lines of constant relative humidity, and they're going to be curves that start in the upper right and move their way down to the lower left. The 100% line is the far left edge of the chart. 0% is going to be the bottom of the chart, the horizontal bottom of the chart. And then you'll see lines 90%, 80%, 40%, 30%, and so on. Then there'll also be lines of constant enthalpy, H. And you'll read those on the left-hand side. And they'll curve down from upper left to lower right. You'll also have lines of constant specific volume, V. Remember, specific volume is just 1 divided by the density. So it's 1 over the density. It's a measure of density. And the specific volume is also done in per pound of dry air. So it's cubic feet per pound of dry air. Not total air, but dry air. Just like your enthalpy is. And then we'll have lines of constant wet bulb. And those may be a little hard to see because they're going to be very, very close to parallel to the lines of constant constant enthalpy. So a line of constant dew point, or a wet bulb, a line of constant wet bulb is roughly a line of constant enthalpy. So you can keep that in mind. We have the saturation line, that's the far left-hand side. And then I can read my values from a particular point by just moving on my chart with lines of constant, whatever the property is. And so if you have a point, you would measure W by going across horizontally to the right and reading the W. To read dew point, you would take that point and go to the left until you intersected the saturation line and read the temperature. If you're looking for wet bulb, you would follow the line of constant wet bulb up and read the temperature, and the same thing for enthalpy. And so let's look at an example here. So if we have a room that's maintained at 72 degrees dry bulb and 58 degrees wet bulb, determine the vapor pressure of the water in the space. And I'll let you think about that for a second. Okay, so we can find the vapor pressure of the water from the expression phi, relative humidity, is PW over PW sat. And so I can do a little manipulation and say that the partial pressure of water vapor is phi times P sat. Now I need to use my psychrometric chart. And so I will look at 72 degrees along the bottom line and then go up until I intersect the line of 58 degree wet bulb. And where those two cross is my point. I will look up a relative humidity, and then I can look up P sat from the steam tables at 72 degrees. And at 72 degrees, I have PV, P sat, PW is 0.39 psia. And my relative humidity is about 43%. And so I can then plug those numbers into my relationship. 0.43 times 0.39 psia, and I come up with my answer, 0.17 psia. It's difficult, sometimes it's difficult to read the psychrometric chart accurately and to get numbers. Is it 43%? Is it 42%? Is it 44%? Don't worry about that so much, because the answer should be far enough apart on your exam that even if you're off by 1%, 1 or 2%, you're probably okay. Let's look at a second example here. 72 degrees and 58 wet bulb, same as we had before. Now we're going to determine the specific humidity, the specific volume, the specific enthalpy, and the dew point temperature. And so we go back to our psychrometric chart and we look at our point that we had plotted, around 43% relative humidity. And now we just look up the rest of the properties. And so if I start at my point and I go horizontally to the right, I can find my specific humidity, my humidity ratio, is about 0.007. And you'll be lucky to read much more than 2 decimal places. 70, 69, 71, something like that. I can then read my specific volume is 13.54 cubic feet per pound of dry air. And the chart that you have in your reference handbook is actually pretty good because it delineates specific volume in fairly small increments. 13.5, 13.6, so it's somewhere in the middle, maybe not quite in the middle. Enthalpy is right at 25 BTUs per pound of dry air. And then dew point is going to be 47.5. So you would take your point and then you would proceed horizontally to the left until you intersected the saturation line. And then you read the temperature. You read the temperature at that point, and it's somewhere between 47 and 48 degrees. I'd recommend making up some more values, different temperatures, relative humidities, dew points, wet bulbs, and then trying this and reading the rest of the properties off. This is a very important skill for doing a lot of the problems in the test and in air conditioning in general. And it's good practice just to give it a try. Okay, so that will conclude this lesson, and I hope it's been helpful, and thank you for your time and attention.